All right, welcome back, everyone. I'm very happy to introduce the next speakers, Yuliya, Sapega, and Joanna Pasiarska. They have been working on privacy-enhancing technologies in real projects. As we know, data and privacy is a very hit topic now, and Yuliya told me that today's talk is all about practical in daily life. So I'm super curious now. Let's give them a very warm welcome.
Thank you. So, as announced, our talk is about privacy-enhanced technology and practical implications for data science. Now it calls AI. So, first about us. Yuliya Sapega, I have 15 years of experience with analytics, data science, and also leading departments which deploy data science, analytics, and AI solutions. And Joanna is with me.
Yeah, I'm Joanna Pasiarska, and currently I'm a master's student, and I'm studying artificial intelligence and medical informatics, and I worked with Yuliya in the past few months.
So this research was done by 3 people, not only me and Joanna, but also with Nadia. Nadia Khalifa is here, but because we had only 2 places to present, so if you have also questions for differential privacy, Nadia can answer all your questions. So motivation. Why do you need to know about privacy-enhanced technology? Actually, let's just crunch our data. We can use AI and agents and just go ahead and deploy it. So in my previous 15 years of experience, I observed that there is not only technical obstacles, there are also organizational and privacy obstacles. It means that you use a lot private information which has sensitive information, and then if you do not take care of it, it can happen that you are not allowed to deploy your model or your data product because you do not comply with the laws. So please first use this QR code and you can ask questions to us because we are very curious. What is it for you? Do you have needs? Do you have feedback? If we do not take care of all questions, we are really curious about your feedback. And after the talk, there will be quiz. And the most active person who will be fast, you can win a T-shirt of your choice. So while you are using QR code, I would like to ask you who knows anything about privacy-enhanced technology, anything, even the word. Okay, thank you. Who is working at the tech teams? Who is data scientist, data engineer, data analyst? I can also use another hand. Cool, so we have a lot of technical people. Thank you. So let's cover the basics. What are privacy-enhanced technologies? As the name of this, well, it applies. It is about technology. It can be Python package. It can be a method. It can be a SaaS solution, sometimes even hardware. So it's anything technical with a single goal to minimize the use of personal data and to protect identity. So everything what you do and use this technology for is to minimize usage of personal data and, again, protect identity. So you can comply with GDPR, AI Act, et cetera, et cetera. There are a lot of rules and regulations. I roughly see 3 different ways to approach this. So you can minimize usage of this data by anonymization. You know all about this. You just get rid of your sensitive information. Pseudonymization, differential privacy. We will explain later about this. So you minimize your sensitive data. Second approach is that you securely take care of this data so that afterwards there is no sensitive information in your data set. And the last one is you limit access to your data. Most of the times, techniques combine different approaches. On the left side, you will see core pets. In orange, there are techniques which Joanna will take care of. She will explain how it works. And on the left side, you will see more advanced technologies. And at the end of my presentation, you will see also techniques which I observed last year beyond Python. So you will see also other possibilities. So let's go ahead with federated learning. Yes.
Yeah, so the first method I will discuss is federated learning. And in simple terms, it's a method based on deep learning, but I have visualization to explain how it works. So first, let's have a quick recap of what deep learning does, just so we're on the same page. So we have some model, and then we have probably it's pre-trained already, and we have some data. So we feed this input to our network, and then we get some kind of results. And if we're not fully satisfied with it, then we can inform our parameters, and then we can fine-tune it. And we can do it until we're satisfied with the result, and then we go back to a validation set, and we ask the same question. And if everything went well, then hopefully our result is much more accurate. And the next statement might be a bit obvious, but in order for this to work, we actually need to know the data. We need to have access to it. But what if that's not the case? Can we still learn anything, or can we improve our network? Or what if there are many institutions that could contribute to what we're doing, but none of them can share data with us because it's too sensitive? Then, as a lot of you are working with data, you know that you can't really do anything because machine learning models are data hungry, and you can't really do anything if you don't have access to it. So that's where the federated learning comes in. So on one side, you have the model, and on the other side, you have data clients or data owners. And what you can do in this situation is you can put a server in between where you upload your model. And then once the clients are connected to the server, they can receive your model. And now that's the key part of federated learning, that this whole training that I described before is happening on premises of data owners. And the important part is that once they receive your model, they run exactly one round of that training, and only one. And after that, the parameters are collected, and they are sent back directly to the server. And now some magic will happen here. It doesn't matter what exactly, but the point is to aggregate all of these results. And how you do it, it depends on your method and your goal. But once those parameters are aggregated, then you can update your main model. And the main difference is that in deep learning, you're looping in here. So this is one training round, and it goes one after another. But in federated learning, one training round goes like this. So you always need to pass server. So you always need to update the parameters, and then you need to download the updated model. And once this is done, you have a network that you can use. And now you might wonder, is that really it? And the answer is that that's it. And we not only research this method, but we also research what can work, and we implemented that in practice. And those are some of the libraries that we selected. In general, there are many more available, but we focus on those 5, and the criteria that we included while selecting those libraries were, for example, is there documentation available? Is there any support? Or is it actually a mature library? So are there any errors or things that are not fully developed? So this way, we ended up with those 5. And we not only implemented them and checked how it works in practice, but we also rated them. And this is a little bit of a subjective rating, and it's trying to answer a question: if I'm new to this method, which package should I look for? So here, the best one is Flower, and that's simply because there are many, many notebooks and tutorials that you can use. There's a lot of support, and if you're new to this method, you can either start from scratch with implementing federated learning, or you can put it on top of your ready project, so it's very flexible. And the second one that I'd like to point out is PySwift, and even though it has 3 stars, don't get discouraged from that. That's mainly because it has very manual approach. So, for example, if you're more focused on the research and you want to develop some new things, then you probably should go for PySwift because that allows you for all this flexibility and adding everything however you want. So it all depends on your use case, but those are general our recommendations, like all of this works. But of course, nothing can be too easy, and there are some challenges that you need to keep in mind. First of all, there are variable dependencies. As you might have noticed in this whole process, you are very dependent on your clients. So it might be a problem that they're not updating parameters at the same time, or they don't download the model. So that's everything that you need to think of while designing your workflow. Second of all, you're working with machine learning methods, and you need to know something about the data, but in here, you don't have access to it. So you can't make any assumptions about, for example, distribution or batch size. So that's something to consider while designing your algorithms. And that brings me to the second challenge. If you don't know what your clients have, it's very easy to get exposed to, for example, malicious clients who have poisoned data. And then, as you saw on the previous slide, you always aggregate all the parameters. And if you don't take any precautions against it, it might be the case that you implement all of it in your final model. So of course, you want to avoid it. And the final thing I'd like to mention is, might be a bit confusing, but federated learning, despite being privacy-enhanced technology, is actually not privacy complete by itself. And that's because you are aligning with principle, I'm not seeing the data, but this whole workflow is not secured in any way by design. It only allows you to work on data that you don't have. But for this one, in practice, there's a very easy solution. You just add another privacy-enhanced technology to kind of secure this whole workflow. And you can do it by, for example, using differential privacy, which is the next method I will discuss. And in very simple terms, it is carefully calibrated noise added to your data set. But let's look at an example. And in general, you can add it on any type of data. But just to make it very simple, I'm using this type of data set. So let's assume a scenario where this data set leaks, and someone wants to know who those people are. So let's look at this one record. And what we would do in this situation is we would go to the whole population of Elizabeth Street, number 58, number 32, someone who's 50 years old, and goes to hospital pretty often. That's probably one such a person. So this data, even though there are no names, we still can pinpoint who that person is. So that's why we are applying differential privacy, which is that designed noise. And in this situation, we categorize our age and might make our addresses more fuzzy. It really doesn't matter how you apply this noise. That's more to the later part with the libraries. But the point is, you make this data noisy. And the question is, can you find the same individual now? So again, we're looking at the same record, and we go into the same street. But now it turns out that there are multiple people who are in their 60s and who go to hospital pretty often. So now there is no way to determine who that person is. So that's why you're using differential privacy. And now you might wonder, that's really nice that my data is safe, but I wanted to perform some analysis on it, and now it's just some noisy input, and what do I do with it? But the whole point is that you can answer those questions, because adding this noise preserves statistical properties. And you can check it for yourself for this very simple example, that all of these answers actually are correct. And the whole trick is that if you add someone new to this data set, the answers to those questions do not change. And again, you can check it for yourself. And that's because those are statistical methods. They always have this margin of error. So it's relatively simple. And the same thing goes if you remove someone. Again, those are the same answers. And so to summarize it, determining whether someone's is in your data set or not is like flipping a coin. It's a 50-50 chance, so there is actually no way of saying. It's like pulling a stranger on the street and saying, I saw you in my data set, but you actually have no way of saying if that's true or not. So that's why I use differential privacy. And now you may think, OK, that's nice, but how do I apply it? And again, similarly to the previous case, there are many libraries that you can use, but we selected those 7 this time, according to the same criteria I mentioned before, and we also rated them. And this time, we don't have one clear winner. It's very case-dependent. But basically, we'd like to draw attention to TensorFlow privacy, mainly because it aligns with many other techniques, and you can combine it with, for example, machine learning. But if that's a little bit too complicated for you, then we recommend Opacus, simply because it's just more straightforward, and there are many tutorials, many guidelines that you can use, so it's very simple. And again, I'd like to draw attention that the SpySift is back, and that's because that highlights the point I made before. It is very versatile, it is very manual, but that also allows you for a lot of combinations that you can make, and you can combine those methods, and it's just a lot of flexibility. So it all depends on what you're aiming for, but generally, if you're new to it and have no idea what's going on, then Opacus is definitely the one to go. But again, there are some challenges. And this time, I'd like to start with attacks, because differential privacy is carefully designed noise, with design being emphasized. If something is designed, you can look back how it was designed, and then you end up with, for example, inversion or inference attacks. And again, it's out of scope of this presentation to explain how to preserve and how to avoid those attacks. But probably you might think that if I add just more noise, then problem will be solved. But that brings you to the second challenge, which is accuracy-privacy trade-off. If you add too much noise, you eventually start losing those statistical properties. But if you don't add enough noise, then the privacy is not preserved. So we need to find that sweet spot. And finally, if your data set is too small, adding any type of noise will just destroy the whole data set. So you need to be really careful with that. But in practice, it's actually not that difficult. You usually use this method while analyzing data. So for all data analysis, this is the perfect method. And second of all, it's really nice to just pair it with any other privacy-enhanced technology. And finally, if you are new to everything, and as we voted before, everyone is relatively new to this method, if you don't know where to start, how to start, then just start with differential privacy, because it's very straightforward. So from very straightforward, we can move to something very complex, which is homomorphic encryption. And in very simple terms, it is a type of encryption that allows you to perform computation on encrypted data in the same way as non-encrypted data. But let's just look at an example how it exactly works. So we start with our very sensitive data. And as in any type of encryption, we generate 2 keys. One public and one private. Private key is the one that decrypts the data, so we need to store it securely and not share with anyone. The public one is the one that is used to encrypt our data, so that's the one we apply. And then we have something that's not understandable for anyone. So now, according to a principle of homomorphic encryption, any computations that we might to perform on this data should be exactly the same as computations that we would like to perform on our original data. So if we give this encrypted data to a data scientist, they should be able to run all the computations. And they do it with help of evaluation key. And this one is generated at the same time as public and private. And the only thing that it does is, because this encrypted data is so complex and so heavy, if we start to modifying it, then it's relatively simple to just mess it up everything and have no idea anymore what's going on, and even our private key wouldn't help. So that's why we have that evaluation key, and then we are making sure that the computations are correct. And we get our result, but because it was performed on our encrypted data, the result is also encrypted. And the only way to get our real result is to request access to a private key. And then we end up with our data. So basically, data is sensitive, so we need to go through this whole loop. But the result is exactly the same as if we went for sensitive data and applied our computations. And now you might ask, OK, how do I make it work? Our research did not include implementing homomorphic encryption in practice, but we did have a look what could work. So I cannot advise you which one you should use or how it works, but I just give some recommendations that those are options. And in practice, generally, homomorphic encryption is used for storing data with goal in mind. In the future, I will perform some computations. But that's generally speaking. And finally, we can go one step further, which is secure multi-party computation. And this one can be a little bit confusing, so I'll just show an example. So we are back with our first data set, but this time we have a random ID. And that's because we're going to split this data set. So just follow me, and hopefully you'll understand the principle of it. So we get our random ID and one of the variables, and we create first data set. And since we always want to find our participants, then we always need to take random ID and another variable. So that's how we create second data set, and finally, third data set. And now, since multi-party computation is a cryptographic technique as well, what we're going to do is apply some cryptographic techniques on those new data sets, and those are called shares. And now, we have our three parties with encrypted data, so those are our shares. And in general, in practice, it could be that those three shares are three separate institutions. It could also be that there are many, many institutions that split their data and they make collective shares, or it could be the example I just showed. But it really doesn't matter. The whole point is that data is split, and you have access to only one share. And now, you're a data scientist, and you have a question that you want to answer. And now the question is, can you answer it if, let's say, you have access to only two of those shares? So what you are looking at are those two data sets. In practice, you're actually never looking at them because they are encrypted or just secured in some way. So that's only for example purposes. So if you have access to two shares only, there is no way of actually answering this question because there's no information about the neighborhood, and that's what you're asking about. And the same thing goes for example, having only share 1 and 2. Not possible. Share 2 and 3, not possible. Or when one of those shares is still not possible. The only way of getting an answer is looking at the whole data set, or all three shares, because that will give you a full data set. So to summarize, in multi-party computation, you need strict collaboration of all the parties in order to retrieve any kind of result. And again, this is only for kind of illustrating what happens, but in practice, you never see this data set. Like what you're working with, it's always this. So that's when solution is possible. And now, again, we did not implement this one in practice, but we just had a quick look what could work, and that's what I'm sharing with you. But again, I cannot advise you on anything. And what about practice? Again, it sounds a bit complex because before I mentioned that homomorphic encryption is so difficult, and now I'm telling you that this is so complicated, and now you have to also collaborate with everyone. But in practice, it's actually used to develop really great things. For example, if there are multiple hospitals and they're trying to develop a new medication, the only way to do it is to collaborate with each other. Or in finance, if you're working on a fraud detection algorithm, then as a financial institution, you don't want to share your data with others, and not with data scientists. So this method allows you to do it. And I talked a lot about it, but who's actually using it? And you probably know all of these companies, and all of them are using privacy-enhanced technologies on tools that you probably used. If you ever type on your phone, and you probably did, you also probably tapped on those smart recommendations, and they are possible because someone used privacy-enhanced technology. Or if you were getting impatient on your Uber drive home, and you were looking at your phone where you are, you probably wouldn't be so happy if you knew that developers of Uber were also looking at where you are. But they don't, because they're using privacy-enhanced technologies. And the last remark is that Microsoft and Intel, they not only use pets in their work, but they also develop them. So to summarize everything that I said so far, this is a quick lookup table. If you don't know where to start or what kind of method you should reach for, then this is like a very quick guideline. And just to maybe clarify, secure multi-party computation and federated learning, the main difference is that secure multi-party computation is dependent on number of parties, and it mainly focuses on computations. Then you can, of course, apply some machine learning solutions, but it's not the key focus. And the final remark is that always use them together. It's hardly ever in practice that you're using only one technique. You're usually going for at least two. So as I said before, federated learning with differential privacy, or yeah, any kind of combination is possible. The point is always use those together. And why would you do that? That's what Yuliya is going to tell you about.
Yes, thank you. So if you want to have more details on practical comparison of differential privacy and federated learning packages, because we did it, we run those packages, look at our GitHub and you will see more details for your particular use case. So, and now about benefits. Obviously, number one benefit is compliance. We are in Europe, even outside of Europe, you cannot escape it. You need to be compliant, otherwise your model or your data product will not see the light of deployment, or even data which you would like to use for your modeling will not be allowed to use, so you will not see this behavior in your predictions. But if you will try to play with those pets, you can figure out, okay, which combination, in which use case you might get benefits of it. These are Python packages. They are totally free, open sourced, and they are updated by the community. So feel free to try on different shoes. So compliance is number one. Another one is, personally for me, I would really like to see that big tech and technology companies really respect my privacy, and I want to trust them. So if they use my data responsibly, I think I would prefer to use this technology over technology which sells my data and does whatever things with my data. So trust is also one of the interesting considerations for using pets, and also operational. In my experience, I had a situation where we had perfect computer vision model, but because we use data which are not compliant, we didn't know it. After 1.5 years of fine-tuning of this model, our privacy officer decided not to allow us to go live, because otherwise we will have problems with the law. So really, I think it's better to cover the basics in the beginning and not later. So, as I mentioned, I do not see pets and compliance as blocker. I see it as kind of precautious, something that is like safety belt. If you want to go fast in your process, first safety first, and then you go full speed. It's not about, okay, how am I allowed to use this data? It's what can I do with this data? Bonus slide. So during our research, we focus on Python packages, but because Python and this technology comes from academia, I observed this, that big tech and well, market moves now to production. So if you combine this technology, pet technology, with Gen AI, you can also have layers of different pets plus Gen AI to put it on hardware or software. It depends on technique. You can have very good output. I have 1 minute, but I will try to explain first one. So synthetic data is a well-known technique, but it is considered as a kind of plain data. But if you do it together with GenAI, you will really have a very good correlation in your data set, and even your privacy officer would allow you to use it in production. I have no time to go through this slide. If you have questions, you can approach us. So we have a time for the quiz, or no? Because there are questions. Yeah.
It's not working. Oh, yeah. Thank you for the great talks. Let's give them a warm applause. Thank you.
GitHub.
So about the questions, I already see several questions from the quiz. Do you want to check one or two of them? And we could take.
Otherwise, yeah.
Yeah, we could take one more from the audience.
You ask questions.
Yeah, maybe audience first. Yeah, could you? Yeah. These questions here.
Thank you for the talk. I have a question about like I think the first method you talked about, the differential one.
Privacy.
Yeah, it seems to me it's like, yeah, you're choosing to lower the data quality of your data set, yeah, in trading off privacy. But it's not really clear to me in what situations you would choose that method over the others. Yeah, so that's my question.
So generally, differential privacy is used in data analysis. So you have a data set, and it is very sensitive. So let's say you're working for a hospital, and they can't really disclose to you the patient's data. So what you can do, you can apply this differential privacy, because applying this noise does not change statistical properties. So for example, if you're interested in how many patients suffering from this condition, or what is the distribution of certain variable, that's still possible. The only thing that you're actually doing with differential privacy is that you cannot identify individuals, but you are not actually destroying the data set as it is. You're only adding this noise, so you cannot identify. So the other way to think about it is just shuffling everyone. So if you switch two people and their age, and for example, with the third person, you also switch the address, then you don't know which variable or which information is true, but it doesn't actually changes anything about your data set. So you still can answer everything about it. So you would choose it over other methods when you're focusing on data analysis and you don't really want to do anything else with it. Is that clear in any way?
Yeah, that's very clear. Thank you.
Yes, that's. I see a question here.
Thank you. I was wondering, so the privacy enhancing technologies you've showed, aside from maybe federated learning, seem to mostly apply to structured data. And how would you handle, what are some privacy enhancing techniques you recommend for dealing with unstructured data? So for example, documents that might contain privacy sensitive information. And I saw some things with the more advanced techniques about LLMs, but just consider that generally when those documents contain privacy sensitive information, customers do not want you to send it to an LLM. So that's not really an option. How do you prep that data so that you can use it?
Can I take this one?
Yeah, of course.
So you say, I assume that this technology is useful for structured data. Structured data is numeric, right? Unstructured is
tabular.
Okay, so this is, I think, assumption which is not totally correct, because if we take a text, which is unstructured data, also images, so you can use technique where the sensitive information is not even in your data set, but you can preserve the correlations or the properties of your data will be in the data set, but it will not point to the person. Sounds weird, but
And
you can do it.
Then what kind of techniques do you recommend for that?
Well, it depends on your really use case, because I cannot give you all-you-can-eat answer. You really need to know what kind of data do you have, properties and what is it you are looking for in your output and how you're going to use it. So most likely you can use differential privacy or federated learning, I don't think so, but I think one of the, where you do not see the actual person itself, so you can insert the noise, or you can, before it goes to your data set, you extract this or substitute your sensitive information before it goes to data set or to solution, and then you can do whatever you want with this. But you will know the information which you will use later, it is in your set. So you can have intelligence, but not knowing who is it, I don't know, Jan Smith or...
How do you extract that? How do you remove it?
You use one of those techniques.
Can I add to this?
Yeah?
Can I add to this?
Yeah, sure, of course.
So the first thing that you could do is, I mentioned federated learning, but you can also use the same principle as federated approach in general. So if this is too sensitive, you can, for example, communicate with the data owner and, for example, suggest that you can write an algorithm that extracts the data, so you probably need to go for a little bit more traditional machine learning approach, probably a bit more manual, but you're just writing a script that extracts the data, and you send them that script, and then on top of that, you would apply, let's say, differential privacy. So you're writing something that would, let's say you have PDFs, and you write a code that extracts all the information, then you are applying differential privacy, and then once this result is approved by data owner, then they can send that data to you, and you can process it further. So you're not seeing data at all, but you're still able to extract it without compromising the privacy. If that makes sense.
Okay, it does kind of make sense, but well, it's not still a full answer to my question, but I think that's a bit long for now.
Can you? Yeah. We can talk later, and then I will get more information. We can advise you on this.
Yeah, I'm afraid we don't have time for more questions, but you could reach out to them personally.
Yeah, we are here, and you know our names, so totally open to your questions.
Thank you
Thank
again.
You very much.
And we do have
gifts
for the speakers.
Awesome. Great.